Well, good afternoon. It's a pleasure to be here representing Vanderbilt University and talking to you about how nuclear power fits into a sustainable energy future. Since this is the only presentation at the Symposium on what's being done to improve the sustainability of nuclear power, it will by necessity be at a fairly summary level. I would also like to note that the summary is mine. It does not represent the views of my research sponsors, so that any mistakes are mine alone. Where's the clicker? Oh, okay. All right, so there's the title. I'd like to start with just an outline of what I hope to present this afternoon. I'll start with placing the present status of nuclear power in perspective within the United States and how it has worked to renew itself over the last 2 decades. Then I will describe the overall structure of research and development as it pertains to nuclear matters in the United States, and I'll also describe what I believe to be our 2 major challenges that the nuclear industry faces in the near future. I'll move on then to describe the role that the Southeast plays in the nuclear industry. I'll look to where R&D support or R&D is conducted in the nuclear business, and finally some trends that I see in R&D in the nuclear business. It has been the policy of the United States over the past 2 presidential administrations to aggressively pursue new sources of domestic energy production. The present administration has referred to this as an all-out and all-of-the-above strategy. Well, what has this meant to the nuclear business? It's meant a renewed commitment to research and development on a broad range of technology challenges that the industry faces. It's also meant renewed support for the present implementation of nuclear power. When we're looking at energy policy, it's important to understand the sources of energy are not all created equal, if you will. A critical difference, for example, is what the source of energy can be used for. In this example from the from the Energy Information Agency within the Department of Energy, we can see that nuclear energy is used exclusively for the generation of electricity, and coal almost so. On the other hand, natural gas use is distributed fairly evenly between industrial and residential use for heating and electricity generation, with a small but growing portion going to transportation needs, where petroleum products remain dominant. Another consideration can be whether a source of power can also be used in some other manner. For example, oil as a basis for a substantial array of petrochemical products. Thus, as Dr. Baldwin discussed this morning, electricity generation is just a portion of the overall picture, but since that is the dominant era of importance for nuclear, that is what I'll be addressing this afternoon. So the question logically comes out in a symposium based on sustainable energy, where does nuclear power fit? First, we should note that as major sources of electricity go, nuclear energy is the dominant provider of emission-free power in the present mix. The present implementation of the nuclear fuel cycle in the United States and the dominant process worldwide is called the once-through nuclear fuel cycle. This means that nuclear fuel is used in a reactor just a single time and not processed or recycled to extract the significant remaining energy content. Substantial energy has gone into the last 2 decades, making this fuel use more efficient, however. In several countries, France, India, and Russia, they do recycle their nuclear fuel at least once, and this provides more efficiency in fuel use and, importantly, reduces mining requirements, which is a very energy-intensive industry. With the present number of nuclear reactors operating worldwide, and that's about 440, available uranium resources are sufficient for about 100 years or more, depending upon future efficiency gains. Options exist to extend this time period. Fuel can be recycled, as I already mentioned, and there are even more aggressive strategies, including the potential use of breeder reactors, which produce as much fuel or more fuel than they use. Also, thorium, much more abundant than uranium, can be used in its own nuclear fuel cycle. So where are we today? Nuclear power has provided about 20% of generated electricity in the United States for more than 2 decades, reducing our nation's carbon footprint. It's interesting to note that this is a time period where not a single new nuclear power plant was brought online, and yet power production has increased over that time period in excess of 30%. The growth in generation capacity has been achieved by better understanding of the technology of nuclear energy, specifically taking advantage of 3 major technological trends. First, and most importantly, more powerful computing, which has permitted better modeling of the reactions that occur within the nuclear core. More accurate instrumentation has allowed us to make better use of design margins, and improved fuel has extended the life of and the time period that we can have in between refueling outages. Over the past 15 years, this more accurate knowledge of reactor operations has added the equivalent of 6 large power stations in the U.S., as you can see from the graph on the right of my slide. In parallel, better management of maintenance and refueling outages has allowed the industry to increase the fraction of time that they are producing power, known as uptime in the industry, from 70% as recently as the mid-1990s to about 90% at the present time, and that's been a consistent trend, that's been a consistent percentage for in excess of a decade. When coupled, these 2 trends have allowed the growth in nuclear power generation to roughly parallel the increase in electricity demand for the past 20 years. As indicated on the right-hand side of this slide, there are still some more what are called upratings in process with the Nuclear Regulatory Commission, and more may be developed as we continue to refine our knowledge of light water reactors and light water reactor fuels. Well, that's kind of the present. What does the future look like? Well, first, the vast majority of nuclear power plants have either completed or are in the process of completing relicensing. This is a formal process that involves major nuclear safety review and independent reviews by the Nuclear Regulatory Commission to permit a power plant to operate 60 years instead of the original licensing time period, which was 40 years. And several new plants are under construction. The Nuclear Regulatory Commission has approved license applications for 4 new design nuclear power plants at 2 sites, both of them in the southeast, at Plant Vogtle in Georgia and at the VC Sumner site in South Carolina. Construction has started at Vogtle, In addition, the Tennessee Valley Authority is completing construction at a reactor at its Watts Bar site in eastern Tennessee. The construction on that plant was stopped in the mid-1990s. When that plant comes online, scheduled for about 2015, it will be the first new nuclear power plant in the United States to come online in more than 20 years. Another 10 projects involving 14 reactors are at varying stages in the planning and licensing process. The exact future of these projects obviously will depend on a number of variables, not the least of which is probably the price of natural gas over the next decade. The Department of Energy plays a major role in research and development in nuclear energy. This leadership role has twin roots: history and the unique hazards that handling radioactive materials entail. Throughout much of the 1950s, the government, through its agent, the Atomic Energy Commission, maintained a monopoly on nuclear materials. Even as that policy eased, the challenge of safely handling radioactive materials has led to the Department of Energy's national laboratories, which were purposely built for handling nuclear materials, to maintain a dominant role. Today, the Department of Energy continues its major role in nuclear research and development, with the Office of Science sponsoring basic research in physics, chemistry, and the materials science topics, and the Office of Nuclear Energy following up with applied research. DOE's Office of Nuclear Energy has established its top-level plan for research and development, shown here in the middle of my slide. And also, the Electric Power Research Institute leads industry research, and I've included an example of one of EPRI's reports. This is a joint workshop on the fuel cycle that EPRI and Vanderbilt co-sponsored last summer to look at risks and environment and safety impacts of the nuclear fuel cycle. As an example of research and development planning in the nuclear industry, here are the top-level objectives of DOE's Nuclear Energy Research and Development Program. You can see that sustainability is prominent as one of the 4 top-level goals of DOE's Research and Development Program. Efforts in sustainability ongoing right now include making breakthroughs in the technology of extracting uranium from seawater, providing science and technology needed to continue to support extended licensing and longer-term storage of spent nuclear fuel, the development of new, more efficient, safe reactor designs, and determining the research and development needed to support the nation's next nuclear fuel cycle, to name just a few items. How does R&D get done in the nuclear business? Well, as I've already mentioned, by far the biggest player are the Department of Energy's national laboratories, represented in the southeast by the Oak Ridge National Laboratory outside Knoxville, Tennessee, and the Savannah River National Laboratory in Aiken, South Carolina. The national labs are the major focal point of nuclear energy research, and they are encouraged to develop relationships with universities in their areas. For example, Vanderbilt shares a collaborative arrangement with the Oak Ridge National Laboratory. A little bit newer is the Nuclear Energy University Program, or NEUP. This is directly focused on encouraging university-led research in the nuclear business. It is congressionally mandated. It is required to be budgeted at 20% of the level of research and development funded in the Office of Nuclear Energy. This means that NEUP has competitively awarded over $140 million in research projects led by universities over the last 4 years. The Department of Energy's Office of Science has periodic calls for research proposals in the areas of heavy element chemistry and in separation science. At a more modest level, the Nuclear Regulatory Commission administers grants through the National Science Foundation in the areas of nuclear science education and technical research in support of nuclear regulation. But the future of the nuclear industry is not without its challenges. I will briefly mention what I believe to be two of the major challenges. We are approaching the second anniversary of a devastating earthquake and tsunami that ravaged the northeastern portion of Japan, killing tens of thousands and severely damaging the infrastructure of that area of their country. The damage caused by the tsunami started a series of events that led to substantial damage to 3 of the 6 reactors at Tokyo Electric Power's Fukushima Daiichi power plant. Exceptional efforts by the on-plant staff helped to limit the amount of damage that occurred, but the releases of radioactivity that occurred have only been exceeded in the history of the nuclear industry by the accident at Chernobyl in 1986. While containment and cleanup are continuing at the site, independent government agencies and safety oversight groups, such as the 3 that I've named, I guess I'd named 4, the 4 I've named there, are ongoing. And along with those groups, there are the groups that own and operate nuclear facilities are evaluating what can and must be learned to continue to operate nuclear facilities more safely. Lessons have been learned to date in the areas of facility management, facility operations and design, and the evaluation continues. And in the United States specifically, we experienced a major course change in 2009 when the license application for the high-level waste repository at Yucca Mountain was withdrawn from consideration. And I need to note at the moment that this remains under litigation. However, the Department of Energy has moved forward with a revised strategy, responding to the recommendations of the President's Blue Ribbon Commission on America's Nuclear Future. They are planning to site and build a consolidated interim storage facility for spent commercial nuclear fuel within about the next 10 years, and to site and start construction on a geological repository for high-level waste by about 2048. The DOE is also committed to continued R&D on the nuclear fuel cycle, including research needed to continue to support safe storage and transportation of spent nuclear fuel during this interim period. This path forward will require substantial work with industry stakeholders to move ahead. I've put together the next several slides to just give you a feel for how concentrated the nuclear industry is in the Southeast. On the left side, you see the facilities that process nuclear materials and nuclear reactor fuel. They are very much concentrated in the Southeast of the United States. On the right-hand side of this slide, you can see all of the sites where nuclear power is produced in our area. And finally, on the left-hand side of this slide, I indicate just the major Department of Energy facilities in the Southeast, most notably the Oak Ridge National Laboratory in Tennessee and the Savannah River National Laboratory in South Carolina. I believe that you will agree that the Southeast has a very large presence in the nuclear industry. This presence also includes 30 operating reactors, and as presently mentioned, 5 that are at various stages of construction. With an eye towards the future, 21 individual reactor license applications are on the books for reactors in the Southeast This represents 70% of all license applications for new construction that are under consideration by the Nuclear Regulatory Commission at this time. Each of those reactors represents between 600 and 1,000 direct jobs on the site, with many more jobs during the construction phase. With respect to nuclear fuel processing and fabrication facilities, as I've already noted, all but 2 of the facilities in the nation are in states that are either served by the universities of the Southeastern Conference or adjacent to those states. I would particularly note that the Nuclear Regulatory Commission has recently licensed the next generation of uranium enrichment technology for use at the fuel fabrication facility in Wilmington, North Carolina. Finally, as I've noted a couple of times, 2 major Department of Energy laboratories are located in our area, and their operational missions and research include nuclear materials processing, basic nuclear research and development, nuclear national security missions, and substantial nuclear environmental restoration activities, in addition to the nuclear energy R&D activities that I already mentioned. So what is needed that the universities of the Southeastern Conference can provide? Well, in one professor's summary opinion, quite a lot. These are just some of the major items that came to my mind when preparing this talk. They include challenges in the physical sciences, social sciences, engineering, and management, along with substantial challenges that cut across academic boundaries. For example, at Vanderbilt, in the Civil and Environmental Engineering Department, we have groups that focus on risk assessment, systems analysis, and in the environmental and safety aspects of the nuclear fuel cycle, and comparing it to other energy systems. In closing, I would note that the Southeast is already in a leadership position in the nuclear industry. And if construction of new facilities is any indication, that leadership position is growing. The nuclear power industry requires a solid and enduring science and technical infrastructure, along with the human capital needed to operate and build these plants. Our present understanding of what happened at Fukushima, coupled with input from the President's Blue Ribbon Commission, reinforce that successful use of nuclear technology requires multidisciplinary contributions, exactly the environment that exists in the universities of the SEC. Thank you. On the next slide, I've listed some references, and for those of you who may wish to read further on the subject, and I'll be happy to take your questions.
Thanks, Steve. Now it's on. This is open for a discussion. And if you have a question, raise your hand, wait for a microphone. Back there was the first hand. Microphone on the way.
Thank you. Good afternoon, John Regalbuto from the University of South Carolina.
Hi, John.
Could you comment on the sustainability of nuclear energy, especially from the standpoint that the fuel from light water reactors can be recycled and run into a breeder reactor? What are we saw the figure here of 100 years, but if you consider the recycling in that sense, you know, how much more sustainable does a nuclear become?
Well, obviously that depends on the efficiency of the recycling system, but it adds factors, you know, 200 years, 300 years, because In the once-through fuel cycle, we only use in the neighborhood of 1 to 2% of the energy content of the fuel. So if we can recycle that fuel and get the uranium and the plutonium that remains in the fuel, we can substantially extend that time period.
Hi there, my name is Austin from the University of Florida. And I heard you mention that they were trying to extract uranium from seawater. And I was hoping you could just maybe give us a quick elaboration on that. I hadn't really heard of that before.
That's research and development that the Japanese started in the 1990s, and it involves placing large arrays of polymeric fibers in the path of major currents, and the polymeric fibers are designed to have a preferential absorption for uranium. So depending upon the specific process that's set up, they are left in the currents for an extended time period. Then they are retracted, reprocessed on land. And some of the work that's going on at Oak Ridge National Lab, being led by Oak Ridge National Lab, is looking at better absorptivity of those polymeric fibers and being able to reuse them for a longer time period before they have to be disposed of as low-level radioactive waste.
Thank you.
Okay, and there was a gentleman back there who's been nice enough to have his hand up the whole time, so.
Good afternoon.
Good afternoon.
I was wondering if you could comment on the use of thorium as a possible replacement for plutonium or uranium.
It's a question that I get every time I make this talk. I think the major thing to be taken into account with thorium is it is another potential fuel cycle. A couple of important items. Thorium is not a fuel. Thorium has to be placed in a reactor and undergo neutron absorption to become uranium-233, and then that is a fuel. So there are preliminary stages that have to be gone through with thorium before you can start its fuel cycle. But with that said, there are technical differences between the thorium fuel cycle and the uranium fuel cycle. And I think it's fair to say that they don't tip in any way in either direction substantially, but thorium is a fuel cycle that has been operated in the past. It was substantially looked at in the 1960s and 1970s. And with the interest in long-term sustainability of the nuclear business, it's starting to be looked at again as a potential parallel fuel cycle.
Hi, my name is Jonathan Wires from the University of Florida. Pleasure to meet you and speak with you, Dr. Krahn. What I want to ask you is, what is the readiness of the Nuclear Regulatory Commission in licensing some of these newer fourth-generation systems?
Wow. I am not a regulator, so I'm not the best person to ask that question. I can tell you that the Nuclear Regulatory Commission has been planning for more than a decade to put in place the capacity to review advanced nuclear cycles. We have had a dry run on that process with the Nuclear Regulatory Commission having taken the Generation 3+ reactors like the AP1000 Westinghouse design through the licensing process. I think the challenge in going to the Generation 4 designs, which encompass more diversity in designs. They include sodium-cooled reactors. They include high-temperature gas reactors. The challenge is getting expertise on diverse sets of reactors, and I know the Nuclear Regulatory Commission is thinking about it, but they also have time. There's not a Gen 4 plant, as they're called, coming up on the docket in the near future.
Do you think we'll see process heat being used eventually from reactors?
That's a very difficult question, and you know, as we were discussing this morning, the United States is not a centrally planned economy, so it's very difficult for somebody to impose on a petrochemical facility or other facility that has substantial heat requirements to be co-located with a reactor. The best we can do from an R&D standpoint is develop designs that are amenable to providing process heat. And the next generation nuclear plant that is being designed at the Idaho National Laboratory is just such a design that's intended to permit either power generation or providing process heat.
There was a hand here. Who's got the mic for this aisle? I think we're doing aisles.
If you would, a comment or two on modular reactors, where that's going.
Okay, the Department of Energy just approved a research and development project, I believe with a B&W-led team to take their design of what will be a smaller light water reactor farther along the process. That's the first reactor that has been authorized by the department under a research and development program that would allow them to authorize another reactor design. So they're moving forward. They have advantages, most especially in two areas. The first area is potentially inherent safety, because they are small enough heat loads that you could potentially have adiabatic cooling, and the ability to come closer to grid requirements for smaller areas that don't require a large 1 gigawatt plant.
There's a hand over here. Oh.
Hi, my name is Taylor Cook, and I'm with the University of Mississippi. And I was just wondering if you could talk briefly about some of the safety precautions that people are doing research on to make sure that things like Fukushima don't happen again.
Another very large subject, but there are a couple that have come out most early, and those are to assure that the chain of command in making decisions about whether or not to undergo small releases of radioactivity to the environment is clearly understood. The industry is looking at design changes to earlier generation boiling water reactors to make them less vulnerable to that type of accident. And on a slightly longer time frame, the Department of Energy has embarked on a major research and development evolution to look at fuel systems that would be more tolerant to accident environments, that would take a longer time under adverse conditions before they released radionuclides. So that's three thrusts that I can share with you off the top of my head.
We can take one more short question.
Bob Avant, Texas A&M. I've been to Yucca Mountain, and after we spent billions of dollars site selecting it, characterizing it, designing it within a stone's throw of atmospheric testing of atomic weapons, what gives you any solace that we're going to be able to locate another one somewhere else?
Well, at the moment, not much. I mean, I think the Blue Ribbon Commission got it right when they said that there's a substantial retooling of the process that the country goes through to try to locate high hazard facilities that would need to be applied to a future repository site before it was embraced by a community and a state. But that is right front and center in the Blue Ribbon Commission's report as the biggest challenge, and it's one of the reasons that in my listing, I said that the challenges really are multidisciplinary. They are not just technical. They are a good understanding of societal impacts of the decisions we make and the public's reactions to those potential impacts.